Natural language models have focused on words in a traditional sense, but modern communication is more involved. One prominent example is the emoji. Our team's goal is to create effective VSMs for representing emojis. While initially studying emojis might seem trivial, being able to effectively understand the usage of emojis can be very useful. For example, chatbots these days could not be convincing if they aren't able to replicate a real human's emoji usage. Advertisers could also create smarter, more attention-attracting bots if they are able to deviate from pre-programmed patterns. In our study, we attempt to create VSMs through multiple co-occurrence techniques, word-to-vec, and glove. Our evaluation approach is a little difficult as we do not have a gold standard to compare to. We decided to have a twofold approach. We will visualize our results on a two-axis graph and also choose a set of emojis to compare their top similarities. We are working with 200,000 original tweets in America over a 2-hour period. We pre-process the data by replacing all ats with a general at and removing duplicate words. We keep punctuation such as the question mark, period, and exclamation point, but remove apostrophes and commas. We choose to skip stemming because a decent portion of our tokens are misspelled, and agglomerating the tenses of words could lose us important information. Hashtags are also seen as separate to their non-hashtagged versions.
As another pre-processing step, every emoji was singularly counted as a word, regardless of if it had spaces next to it or not. We figured that when users use multiple emojis in a row, they are expressing multiple different semantic ideas instead of just one, so we separated them. To start simple, we used non-deep learning algorithms. We started experimenting with a simple co-occurrence matrix, PMI, and PPMI. In contrast to traditional word windows, we simply assumed that two words co-occurred if they appeared in the same tweet, because tweets are so short after all. To visualize these high-dimensional vectors more easily on our screen, we did PCA on the vectors and only kept the top two components. However, in the future, we learned that tsni would be much more effective in visualizing the dataset. In the end, none of the simple approaches did very well in describing the semantic meaning of the emojis. They'd often just place the extremely frequent emojis off to the side, which makes sense because high counts dominate the co-occurrence matrix. On the other hand, word-to-vec, which does involve weight matrices and a softmax output, performed better by grouping like words with like. These promising results encouraged us to dive deeper into just emojis. However, applying tsni on just emoji embeddings gave us less comprehensible results. Furthermore, finding the closest word association to each emoji using vector arithmetic did not work so well either. Why did word-to-vec work so well on the entire dataset, but performed poorly when we narrowed our focus? Well, looking at the dataset, barely 1% of all characters were actually emojis. So even though we had over 5 million tokens, most emoji types actually only showed up a couple hundred times, which we believe is not enough for word-to-vec to give accurate embeddings. Therefore, our most crucial step moving forward is to gather more data and check that the count of each emoji type is sufficiently high.